Hi-oh, here we are again. Waves. Talking about waves today. What is a wave? Well, waves are basically a vibration moving through space. For example, a vibration, something going back and forth, as you can see on my pen. That's a vibration, but if we make that vibration move through space, look what we get. We get a wave. Now, contrary to popular belief, if you throw something in the water, you might see it move down shore. But the waves are not doing that. The waves are just causing it to bob up and down. It's the currents underneath the water that's actually moving it. So the waves are nothing more than something that carries energy and not actual matter. So the energy is flowing through, for example, the water. Sound is a wave, and it's energy traveling through the air, not the air itself being sent from your mouth, for example, to someone's ear. Two types of waves. I mentioned the idea of sound. Sound is a specific type of longitudinal wave, and those longitudinal waves are exactly as it suggests. The vibration back and forth, is in the same direction that the wave travels. So it's longitudinal. It's parallel. The other type is transverse. The word transverse means cut across. So the vibration is up and down, and the wave travels perpendicular to that. Good examples, as you may be aware of water, but what you may not be aware of, light travels this way. It turns out, of these two types of waves, only one of them needs to have a substance to transmit the wave through, and that's a longitudinal wave, because what's happening is the particles are knocking into the next particle, is knocking into the next one. When it comes to a longitudinal wave, a transverse wave, that's not necessarily the case. For example, light can travel through the vacuum of space. I'll let you read this yourself, and you can pause the video or the podcast and see it for yourself. But I do want to focus on this particular idea, as this is a tough part for most people. Amplitude. Amplitude is that measurement of the energy. The energy, remember, that's what waves transmit. This equilibrium point here is if there's no waves. So let's use water as an example. The water is nice and flat and level. If you make a wave, the wave goes above that equilibrium point and below that equilibrium point. When we measure the amplitude, we're only interested in one or the other. The amplitude is not, I repeat, not from the crest to the trough. It's from the crest to the equilibrium point or the trough to the equilibrium point. Give you an example. High energy, big amplitude, and again, amplitude is that measurement there. Wavelength, as it suggests, it doesn't matter where you pick. Take a point on a wave and find that same exact point. The examples I've given here are just examples. They're not the only situation. For example, if I pick this point right here, I'm on the downswing starting at the equilibrium point. So I need to find that same spot. Again, here it is. A downswing. I'm on the downswing sitting on the equilibrium point. Notice that has one whole trough and one whole crest. The symbol that we use to represent wavelength is the Greek letter lambda. I often draw it like that. We measure, since it's a length, we measure it in meters. We also need to talk about the period of a wave. The period, as you would suggest, or as it would suggest, is measured in time, seconds. We use a capital T. It's a little, can be a little confusing because period sounds a lot like frequency. You see, the period is the time for one wave to go by, and frequency is how many waves go by in a second. Frequency we use mathematically a lowercase f and we measure it in hertz. You've probably heard of this unit before. These two variables are inverses of each other. Period is 1 over the frequency, and if you solve that for frequency, frequency is 1 over the period. So as one increases, the other decreases. Pause the video, see if you can answer these questions as they go, and then wave velocity is something else we need to concern ourselves with. Velocity is frequency times wavelength. You've always known velocity to be distance divided by time. Believe it or not, this is a distance divided by time. Wavelength is measured in meters, and frequency, if you remember, frequency is 1 over the period, so 1 over the period, which is measured in seconds. Meters times 1 over seconds is meters per second. So a little practice here for you. If it takes a quarter of a second for a pendulum to make one back and forth swing, what's the pendulum's period and frequency? Remember, they're inverses of each other. If you know one, you know the other, but you have to know one. We know it takes 0.25 seconds. Sounds like the period to me. And of course, frequency is 1 over that period, and therefore it is 4 hertz. You might want to pause the video and try these couple of practices before you see the answer. Okay, the next one.